4, I guess. All right.
You can move it if you want.
Move it up. You can probably see me a little bit better now. Okay. So I've been working on dust classifications from the weather monitoring stations that Noaa has. And on a secondary project is also using remote sensing and satellite imagery. And I'm doing this for my thesis in the Plant and Environmental Science Department. Some of the challenges about classifying dust is how skewed or the frequency of the dust storms throughout the year. When trying to come up with a classification throughout the year, it's just maybe 15, 20%, even less of the dust storms throughout the year. So trying to come up with a classifier that can give a good representation about that is a little bit challenging. You know, sometimes in the texture of the dust storm itself is a little challenging as well. How do you distinguish a cloud and a dust storm? You know, pretty similar. A person can do it pretty easily. A computer, you might look at the pixel values, RGB, and that's kind of the idea that started off with. We were like, well, let's try to look at the colors of the schemes, and there's just a picture of clear day, a little bit of clouds there, but just one of the cameras that's out there, and that's how a picture of a dust event. And, you know, it just looks a little foggy. So, you know, in imagery, you know, this could be just blurred out or buffy. So it's kind of makes it a little hard to start to distinguish these. Dr. Dubois had several students working on this project where they were looking at videos from the year 2015, and they were making just documentation of what they were seeing. So they were looking at the videos and observing every dust event, recording the certain time and precipitation is present or not. And that takes a lot of time. And by making a classifier, you know, we could just run the videos into the classifier. And this will actually in turn help them by looking at, you know, the weather patterns and trying to find the precursors. So this project will lead up into that, and, you know, could probably help out Jalen a little bit more. If there's more dust events that he can look at, and if we can distinguish the size of them, then he can look at those specific dates and see what kind of weather patterns were there, and see if any precipitation or maybe soil measurements from remote sensing, you know, determine what kind of stuff is going on. And so there is a total of 1,090 videos out of the 5 satellites that are out in the playa that contain dust events. Now, what I was doing is I'm separating each video into each individual frames, and they have 10 frames per second. So by splitting those up, I'm going to have around 9 million frames. And not all of them will contain dust. Again, it's a little skewed, and that just adds to the difficulty of this. The bottom table here, you could see distinguishing of the large, medium, or small plumes. There are a lot of small plumes, and those actually just, they could be little plumes, or they could be dust devils that come and go. That also adds to the challenging. Another thing is the distance. You know, something that's far away will look small from one weather camera. So that can add a little bit of difficulty when trying to classify that. But we got a little bit of data here, and the next, just a summary about throughout the months and the total number of it. So there was a total of 1,727 recorded plumes. 91 of those are large plumes. So definitely going to emphasize on those in my classifier. And I'm going to take the medium plumes as well, 415 of those. So it's going to be pretty good. A lot of the small plumes, I'm going to see how the large and medium works out. And if I'm getting good results, I'll start incorporating the small plumes, but I'm still going to extract labels for each frames because I need to know whether the frame had dust or no dust. So it's a binary classification of it. So I'm still going to do it all and try to extract it all at one point and go back to it if we're getting moderate results. Just another table, just showing the representation of how the dust storms are separated through May through September, observed in the year 2015. So some of the previous work that got me thinking about this a little bit more is there was a paper that I read about traffic monitoring. They were trying to classify the traffic, but they were having problems from day and night where they were having trouble looking at the cars during the nighttime. So they actually had another program to do it, but they needed to find a way when to tell it to start using the next program, especially with time, sunset changing as the year progresses, and then time zone issues where they start changing the time and days. So they came up with a classifier based off of hue, saturation, and value. And what they were able to see is by looking at the hue, saturation, and value, there's certain, in the color spectrum, during the day, you have a lot of, majority of it is in the red color spectrum of it, as you can see here, the red, but there is a lot of green and blue that's still present during the day. And you will see in the hue, or in the value, you can see that it's a little bit brighter, which makes sense. It's brighter in the day, so you'll have brighter pixels. In the nighttime, you'll actually see a lack of the green and blue, which also makes sense because now it's night and the only light out there is from the vehicles themselves. So you're still going to see red out there and a little bit of yellow, but you're going to see a distinguishing mark of the value pixels. They're all going to be in the lower range, so they're all darker pixels, which makes sense. And I was thinking, well, dust storm can block out light in the big storms, so we're going to hopefully see a lack of the value. You see that shift down, and then you'll see a color change too. So I decided to try to follow the same approach, and here's a workflow diagram that I was doing, is where I was taking the archived videos and selecting each videos and changing them into frames. And to try to lower my computational time, I was cropping the pictures to make them a little bit smaller, focusing on the center frame, so the horizon of it. And I was doing the color transformation to hue, saturation, value, just like they were doing. And I was plotting histograms, scatter plots, and I was trying to determine concentrations in these plots, where I would start counting pixels, and if pixels exceed a certain threshold, classified as a dust storm. And this plot here is showing, you can see at the top left corner, you can see a day with some clouds in the sky, and this is just an image of the hue, saturation, and value combined all together. At the bottom, you see a hue and a value image individually and their spectrum. But you could see how in the day, without the dust present, you got value from 0 to 1, and the ones would be really bright with the clouds. And you can see the color distribution across between 0 and like 0.15 and around 0.65 to 1. It's kind of the range that you would see for a non-dust event. Well, here's one with the dust present. And you can see how this area, you start losing the clouds. So that's a little good. It looks a little promising. Now we may not get confused with clouds so much through the value. And the range for the hue is still a little similar. So it still looks a little bit the same. And this is just another example of it. Again, you can see the same thing with the value, and the hue is still a little constant. So the color is not showing too much of a difference. This is just a later day of the picture, and it's starting to get a little darker, so you start seeing even less hue, or there's less of the value, and start seeing the colors squishing together. And this is one with a lot of dust. So this is a frame with a lot of dust in it, and you can see that the value seems to shrink down even more. So in comparison to the night one, it's still dropping and dropping, which is good. It's what we want to see in these large dust events. So this is actually an image where it's plotting kind of a control, non-dust, and then a dust event. The blue is what it's seeing right now, and the red is showing an image that's a little bit clearer in the day with a little bit less clouds and not a dust event present. This is just showing that a little bit more. You can see the clouds. Now you see the blue going up because of the clouds. So yeah, you can see the clouds in there, but this is a dust storm now. And you can see how the value dropped. So that's a good indication of a dust storm. So that's really promising. And you can see that the hue is now shrinking a little bit. So before, when you weren't comparing it to a clear day and a dust day, it was a little hard to determine that. But now when you put them together, you can see there's a little bit of shrinking going on. And that's what I started to notice as dust storms started to appear in these large events. The hue and the value would start to shrink down vertically and horizontally into, the value would be between like 0.4 and 0.65. And the hue had two boundaries between 0 and like 0.1 and 0.7 to 1. So again, that's just referring to the red, violet colors, and then the hues is dropping the light. And this just demonstrates that as the storm gets stronger, they start to shrink down and more. So I think that was a good classification of it. But I was noticing that it was having trouble distinguishing the smaller storms. With large dust plumes, it's easy to tell, but those are important to know. But we also want to try to detect medium-sized plumes and maybe even small ones. And I was thinking of ways to try to get the most appropriate thresholds. And I was thinking of using some statistical methods to determine this. And eventually I decided to just do a machine learning on this and using still logistic regression. Because of the hue, saturation, and value, we're going to add saturation in there to see what kind of missing data we were having there. So by adding hue, saturation, and value, now we have three variables that are going to be trying to predict a dust if it's present or not. So by using a feed-forward neural network and an activation function of the sigmoid function or the logistic regression, we're hoping to take all these three parameters, hue, saturation, and value, and plot it against the sigmoid function to see which threshold will give us the most probability of a dust storm happening and classify that as a dust and non-dust. Now, there is another way we could try to do this is with an unsupervised and try to cluster it. We can just start dumping the frames into it and see if it starts clustering using k-means values or other clustering methods to see if it clusters dust together. And because it's not labeled, we might see precipitation clusters and other clusters of other mineralogical phenomena that you would appear. One thing that I was playing around with just this week is the gray level co-occurrence matrices. One of my buddies came to my office and he was looking at the videos that I was looking at, and he said, by using these GLCM, you could try to determine textures. And this might help you a little bit better in classifying a dust storm by looking at it through texture. So here's an image. You can see an image of the storm or the day, and we have to convert it into a grayscale. And by doing this, I picked 4 points in the sky, or 5 points in the sky, and 3 of them in the ground. And I was just playing around with the code that was already available, and they called it grass and sky. I just left it how it was. And you can see how these grass ones, with the exception of this being in the sky, you can see how it's a little bit darker in the spectrum, and these other ones are in the sky, and you can see they're a little bit lighter. But you can start to distinguishing like shapes into them. And these, the way the pixels are ordered is the way these images. So the first pixel or the first blue dot is, the sky, and then so on. So I think it's worthwhile to explore more of this gray level co-occurrence matrices to see if we can determine this and maybe make another system where I have these gray colors scheme and try to do that with the machine learning as well and see how that works out. Kind of the second project that I'm working on is to do machine learning algorithms, but with the satellite imagery and we're going to be using the GOES satellite imagery, or GO16. And there's actually 4 bands that are of interest. Band number 1 is used to monitor aerosols. So we might be able to see dust from those imagery, and that's done every 5 minutes for continental United States, and it has a 1 kilometer resolution, so it's pretty good. Band 11 is an infrared cloud top phase band, and that's used to monitor volcanic ash and dust. So it's just another way that the GOES imagery itself already is trying to look at dust on its own. So we're going to take that to the 2 kilometer resolution. And Dr. Dubois had a student last year, or about a year and a half ago, Rebecca, who was working on dust classification too, and she was actually using band 14 and 15, and there was actually a difference of those. By taking the difference of the long wave bands and the dirty long wave band of infrared, using the temperature, you can see how there's a dust storm present, and I'll show a picture of that a little bit sooner. So 5-minute temporal resolution, and the spatial resolution is for between 1 kilometer and 2 kilometers. And what this I plan to use is combine it with weather forecast models, or the rapid update cycle, or the rapid refresh, and now its predecessor, the high resolution rapid refresh. And this table just shows how the weather data is distributed. So it's distributed as a grid, and it has spatial resolution from 13 kilometers from the rapid refresh, or RUC 13, which is the one I would use going back in time. And the rapid refresh has 13 kilometer resolution, the HUR has 3 kilometer resolution. So we're starting to get finer imagery and more accurate results of representation of that. And they're separated through isentropic buried layers. So they're separated into 50 layers, from the ground to the atmosphere, and then it started going to 51 at different altitudes. And this table just shows a little bit more information about how many grid points to have. Again, its resolution and how many vertical layers it has, and how it's separated isentropically sigma layers, or if it's just a sigma layer, just separated through altitude. Not too much there, but this is going into Rebecca's work here. So this is a picture that she did of 15, the band difference, and you could see the dust storms there, which is going to be useful because now we could look at that, and you can see that's a little contrast to what you're seeing up here, some cloud cover. So that's going to be pretty good, because now we could try to use machine learning to try to find that shape and that shade of color into that. And this has been done before too with other medical fields, where they're trying to determine like malignant cancer cells using machine learning, convolutional neural networks. And that's the approach that we want to try to do next, is using the convolutional neural network, and by taking these imageries from the satellite GOES, we're going to feed this in here, and we're going to see if it can detect the edges of these dust storms, and then build a model off of that as well. One thing, because again, with the skewness of the data, we could reuse that data to try to train these machine learning algorithms, and by using a recurrent neural network, where it cycles through it over and over, like if you were learning it, and repetition makes practice, and you get better and better at it. So if you keep on looking at the same image, hopefully it will start to recognize, yeah, this is a dust event. And there's also a concept of long-term short memory that I'm going to be going into and investigating about, because this is meteorological data throughout the years. Something that happened 20, 30 years ago may not have so much effect on something that's going to happen right now. Something that happened last week can have an effect of what's going on here. It definitely took yesterday to today. So the concept of long-term memory just represents that it's going to be saving a little bit of its information, but it's also going to be weighing it. As the time series progresses, older stuff will start to get weighed less and less, and affecting the future prediction. So that's another thing that I'm going to be spending a lot of my time in, trying to resource this. So a lot of my time spent this past year is actually just setting up the data to try to fit into these machine learning algorithms. Trying to come up and download the Go's imagery. It's available through Amazon Web Services. So if you make an account with them, you can just start downloading it straight from their website. And the rapid update cycle is available through HTTPS or FTP. So you can just download that straight off of the online too. And I've been learning a lot how to deal with these large data sets and how to increase my computational time. So this August, I actually went to the University of Madison, Wisconsin, where I learned how to use their HTC Condor system for high throughput computing. And this allows me to separate, if my jobs are independent of each other, I can separate my job into a small little task, and I can submit it across 100 computers, running with one CPU. And they'll take a little bit longer to run, but I'll have 100 results right away in comparison to having, a moderate computer taking a few hours to do the same type of thing. New Mexico State University has Josue Discovery, which is a high-performance computer here. So I'm going to be using that. Once my data is ready, I'm going to be using that to train my neural networks. Once I have a neural network trained and I have its weight matrices available, now I can export that and submit it back into HTC Condor and do validation off of that. With submitting that algorithm and with those static weights now, I can submit it across 100 computers or so or more and just send one image to each classifier and tell it to send back its result, whether it is 1 for dust storm, 0 for not. Another thing that I've been having a lot of trouble with is my work environments, from going from HTC Discovery, my computer, and another computer that I use down in the labs. So one way to overcome this is using Docker imagery, or the Docker repositories. And Docker allows me to create virtual environments where if I just install Docker into any computer, and HTC Condor has that, and so does the Joker and Discovery here at New Mexico. So as long as I have a Docker, and I'll make a Docker image, so it's pretty much just a simple build of my environment, I can just upload that and then run my program as just straight directly from that environment. So it makes a small ISO image that has all my environment variables and makes my program run smoothly instead of having to work a little extra to adapt my program to work for a specific HPC cluster. So this allows me to just submit it if they have it and just let it go. I've been using Anaconda to install these softwares of Python and the libraries that I've been using. And the Noaa Weather and Climate Toolkit is actually an open source software that's out there that can help you look at weather data. So NetCF, HDF, and grid data. And that's something I've been looking at to just open the imagery. There's also ArcGIS. You can get your license through that. But this is a nice open source, and that's something we want to try to focus on, is that, HT Condor, you can open a free account through the Open Science Grid. And if you get your account, that's going to be good. There's a lot of HPC clusters out there that you can also request access to, and that's really good. Docker's free, Anaconda's free, and so is the Noaa kit. So once I start to actually train my models, I want to make my code available to people so they can look at it and maybe adapt it to whatever they're trying to do, and see if they can just reproduce my results. So reproducibility, and trying to make this as open source as possible for people to look at. So making my data available is going to be important too. And as the file sizes get bigger, it's going to be a little challenging. But a lot of my time this semester and this year have been trying to get my data ready to make it to these inputs. As I mentioned earlier, I'm going to have around 9 million frames for the year 2015. So now I got to go in there and look at each frame and just put zeros or ones for each frame, then that's going to take some time. But eventually, with the classifier, it's going to do that on its own. So at the beginning, it's going to take some time, but later on, it's going to be really great. A lot of the funding I'm getting is from the National Science Foundation, And just I want to thank my advisors and my thesis committee is Dr. Colby Brungard is my main advisor. He's been giving me guidance and ideas of how to approach this issue. Dr. Dubois, who's also in my committee, he's been guiding, him and his team have been giving me the data and about the dust events. So that's really good. And Dr. Huiping Ko have been giving me just the data, the resources available on campus and the funding. She's actually the one that, from the computer science department, who's got the grant and allowed me to work on this. And now that's the next work of it is just to be, once the data is ready, start making these neural networks. So a lot of this presentation was just talking about my future work, and that's what it's going to be taking. As we know, it takes a lot. 80% of the time is you getting your data ready, and 20% is just analysis of it. And that's my presentation.
All right. Well, thanks. Thanks, Josue. Thanks, Vida.